right, hi everyone. Welcome to NASA's Goddard Space Flight Center. My name is Elizabeth and I am the social media lead for the Hubble Space Telescope here. And today we're live now with some big news from Hubble, and here to tell us more about it, joining us we have Dr. Jane Rigby, who is a co-author on the result we're going to be talking about, and she's also the operations project scientist for the recently launched James Webb Space Telescope. Also with us, we have Dr. Patty Boyd, who previously worked as the Deputy Operations Project Scientist for Hubble, and now works as the Chief of NASA's Exoplanet and Stellar Astrophysics Laboratory. So, I'm really excited to learn more about this new discovery, and if you're watching live, feel free to comment questions during the live show, and we're going to do our best to get to a couple at the end. But for now, I think we're just going to jump right into it. So, word on the street in the astronomy world is that Hubble just broke a pretty impressive record. So, Patty, could you tell us what Hubble discovered?
Sure, I'd love to. It is a record setter, and that's really exciting for a telescope that's been in space for 30 plus years, like Hubble has. And it's based on one of these beautiful Hubble images. You know, they're so iconic. They show so many galaxies. You can see a spiral galaxy flying away there. And then you see these individual galaxies that look yellowish white. They're actually gravitationally bound to each other. They're a cluster of galaxies. And hidden in almost the mists of this image is actually a single star here. That is the farthest single star we've ever seen. The light from that star came off of the star when the universe was less than 1 billion years old. So that is the record, the very farthest star we've ever seen coming at us from a time when the universe was just a baby.
Wow, that's amazing. So just as a refresher to everyone, Hubble has been orbiting Earth for almost 32 years and is still generating incredible science like we just heard about. So Patty, could you also tell us just what can astronomers learn about our universe by examining this star?
Right, so this star is like a window into the early universe and how star formation worked back then. When we look at the most distant galaxies, the earliest galaxies, we're usually just looking at hundreds of billions of stars and their light conglomerated all at once, distant galaxies. It's very rare to see a single star, obviously. That's why this is a record setter. So this is a window into how star formation happened in the very early universe. When you look at a picture like this from Hubble, you see galaxies at all different ages. And those images show us that galaxies actually changed and evolved through the history of our universe. The same thing is true of stars. Stars today are not like stars a generation before or a generation before. This is it is the earliest example of a star that we have. So it's going to be able to help us put into context star formation, generations of star formation, and to really look at the environment that that particular star grew up in and how it's going to shape its environment as well.
Great. So this observation was only possible because of a phenomenon known as gravitational lensing. So Jane, I'm going to ask if you can break that down for us. What does that mean?
Gravitational lensing is just one of the most useful and cool things in the universe. It turns out that matter can warp space-time, right? That's why the Earth goes around the sun, because space-time is warped by the mass of the sun. Well, it turns out that warped space-time, light sees that too. And so what that looks like is that it acts as though gravity is bending the path of light. All right, well, okay, how do we bend, what happens when you bend light? Well, that's what eyeglasses do, right? You're bending the light so that it actually gets in the right part of your eye instead of in front or behind. And so gravitational lensing, it's not just an analogy, it's the same equations that are used to describe a lens, like in an eyeglasses, are used to describe how the cluster of galaxies bends the light. And so what we have here is we have a cluster of galaxies, and then way behind it is a background galaxy, minding its own business, has nothing to do with the cluster. And the light comes around the cluster and is bent by the cluster toward us. And so when Hubble sees this, Hubble has nothing to do with the cluster, the background galaxy has nothing to do with the cluster, but that cluster acts like a natural telescope. And so we see that background galaxy something like 10, 20, 30 times brighter than it really is, and stretched out so we can study it in much greater detail than we normally can. So it's just one of these cool things that there are these cosmic telescopes that we can use in conjunction with the telescopes built by humans to really try to understand what the early universe was like.
Okay, gotcha, awesome. And so when people were making this observation of the star or Rendell, how did they know that this was an individual star rather than a bigger cosmic object?
Sure, so the Lens galaxy itself was found in 2016, right? So this big red arc, called the Sunrise Arc is its nickname, was found in 2016 by Dan Coe and collaborators, and he gave it to his graduate student, Brian Welsh, who was modeling, like undoing the funhouse mirror, figuring out how the shape of the cluster, where the galaxies are in the cluster, gives you the image that we see, that distorted image. And what he came up with was that in all the models, this is a copy of this. You know, he could get this lovely symmetry going on. But this one little dot right here had to be very high magnification and very small, like size of our solar system small. And so you're like, all right, and it had to be pretty bright. It's not, you know, so it was like, okay, you have something that's like about 1,000,000 times the brightness of our sun and the size of a solar system. Well, there aren't that many things that could be. It could be an accreting black hole, but it's not changing brightness. It's too small to be a star cluster. So it really kind of either needs to be a star or maybe 2 or 3 stars together. And they need to be very massive stars, which is super interesting because massive stars are the ones that make all the heavy elements of the universe and that explode as supernovae.
Okay, awesome. Very interesting. So we were talking about this a little bit earlier, but this star is within the first billion years of the Big Bang. So Patty, could you tell us how we know that?
How do we know that from the Hubble image?
Yeah.
That's a really cool story. So the entire image that you see is actually put together as a composite of separate images, each of which is taken through a filter. And so the filter actually blocks a lot of the light and just lets the light in through a certain region of the wavelength spectrum. Some of them are bluer filters, some of them are very optimized to where your eye would peak, some of them are redder than that. Some of them go redder than our eye can see, into the near infrared. And when we put all of those separate filtered images together, it can be stacked and processed so you get a multicolor image. And that's exactly what we're seeing. So you see the colors in all of these galaxies, and you do see a lot of distribution of colors. You know, the ones that look more typical galaxies, you can see some spiral shapes in there of different colors. There are some that look pretty red. And then our strip here, this is actually the lensed galaxy, is about the reddest thing in the image. And that's because the light in these galaxies is actually red shifted as it gets further back. That light, since the universe is expanding, the light itself also expands, stretches, turns red. The further back it is, the further away it is, the redder it gets. And so when you're seeing things that are really showing up as red, their light's absent in the other filters, but it's starting to show up in the reddest filters. And so what we're looking at is the dimmest, reddest stuff in that image. You can take those fluxes, the brightnesses of all the different filters, and you can estimate the distance of the galaxy just based on which filters it's showing up in and which you can't see it in. And so those objects there are consistent with that redshift of 6.2 or so, or 12.9 billion years ago.
Oh my gosh. Wow. So Patty, could you also tell us why do you think it's important that we're studying, you know, cosmic objects that are within the first billion years of the Big Bang?
So it's a really big mystery in astrophysics, and actually the Webb telescope was designed to go after that, you know, area where we don't know a lot about the history of our universe. But why it's so interesting to us is because it answers the question of how did we get here? Why is the universe the way it is today when we look at stuff near us? And what we see around us are a lot of heavy elements. They make up everything that's important to us. The heavy elements are in our bones, in our atmosphere of the planet itself, the telescope that's out in space. These are heavy elements that are heavier than hydrogen and helium, which were the primordial stuff of the Big Bang. And we know that stars take heavier elements and they fuse them and they make things like planets around us. But what's not very well known is the beginning of that story, chapter 1. And so a star like Earendel, which is coming from that first billion years, is going to be able to allow us to peek in there and see how that processing of material is happening in a massive star like this in a way that we can't do with any of the other stars around us.
Got it. Okay, awesome. So another great part of all of this is that there are already approved observations of Earendel with the James Webb Space Telescope, which is a super powerful infrared space telescope that just launched this past December, and we're so excited for it to start science operations this summer. So Jane, I hope you could just tell us, you know, how is Webb going to bring this Hubble discovery even farther?
Sure. So there was a proposal that was approved to study Earendel and its parent galaxy with Webb, and you know, we got like 1,000 proposals, and it was one of the couple hundred that were accepted. So we'll be observing Webb with the Webb telescope with 2 of these science instruments. There's 4 science instruments on board. We're getting them checked out and ready to go right now. We'll examine this galaxy and the lens star with the NIRCam instrument, which is a camera that takes pictures in colors, and it'll start about where the Hubble image stops and then go redder from there. So it'll get those filters that are too red for Hubble. So from that, we'll understand the kinds of stars that are in this lens galaxy, whether those stars formed all at once or in like popcorn over several hundred million years. We'll also obtain with the NIRSpec instrument, which is a spectrograph, a spectra. We're going to divide the light up with a little prism and get spectra of the star and of the lens galaxy. And we do that with these cool microshutters. There's like 250,000 doors on board the telescope. They're really tiny doors, and you can, with a magnet, and you can electrostatically address them. You can say, I want this door, and that door. Open up now. And so that way you can block out, you close most of them, and you block out the bright night sky, and you just open up the doors of the things you care about. And so that means we can take a very, very deep spectrum, the colors of the light of the star and the lens galaxy. And so with that, we can tell what are they made of? How much hydrogen is there relative to carbon and oxygen, to heavier elements? What's it like? What are the physical conditions inside this galaxy as we're seeing, a billion years after the Big Bang?
Okay, awesome. And talking more broadly, why is it important that Webb and Hubble are going to be operating at the same time?
Yeah, so Webb and Hubble are really complementary. They're really different in a lot of ways, and they're designed to do different things. When we built Webb, Hubble was in space flying, doing great stuff. So we were trying to replicate that functionality. So it's really like different players on a baseball team. Your catcher and your center fielder have different skills, and that's on purpose. So with Webb, we're going to be working in the infrared. We're going to be doing a ton of spectroscopy, and but Hubble is still going to be the king for the blue light, the ultraviolet light, that stuff that Webb just cannot do because of its gold mirrors and its infrared design.
Gotcha. Awesome. Yeah, I'm super excited for them both to be working together in space. It's going to be awesome. And bringing it back to Hubble for a second, Patty, could you just sort of tell us how Hubble's doing these days, how long we can expect it to be around for?
Yeah, I'd be happy to. So Hubble is doing great. And one of the main reasons that it's doing so well after 30 plus years on orbit is that it was specifically designed to be serviceable. So it's in a low Earth orbit. It goes around the Earth every 90 minutes. And that orbit is very complementary to the space shuttle orbit. So there were 5 separate servicing missions where astronauts went up in the space shuttle, grabbed the telescope, brought it into the shuttle bay, and refurbished the telescope. They could do things like repair instruments, but they could also do things like get a next generation computer on board, upgrade the power systems. And so that last servicing mission 5, the team left that observatory at the peak of its scientific capabilities. And ever since then, there's been a team of scientists and engineers that are, on around the clock, basically making sure that this telescope can have the most extensive life that we can imagine, because it really is still at the peak of its capabilities. The scientific community is really excited about it still. We still get 1,000 proposals or more every year to do all that cutting-edge science that can really uniquely be done with the Hubble instruments, particularly in the ultraviolet. It's unprecedented there, and it will be for some time.
Okay, yeah, good to know. Thank you. All right, so everyone bear with me for a second. I'm going to take a look and see if we have any questions we can take a look at real quick. Okay, all right. How do you guys feel about talking about when we're looking at this image of Earendel? Is that exactly like, are we looking at it as it existed 12.9 billion years ago, or is that what it looks like now? Like, what is that? What are we looking at?
Right? Okay. Let me take the long view on that one.
Okay.
Okay, go look at Jupiter. Well, not right now because it's daytime, but at nighttime, go look at Jupiter. And you see Jupiter as it looks about 40 minutes in the past, because that's how many light minutes away Jupiter is. Okay, when we get light from the sun, we're seeing that light, it left the sun 8 minutes ago. So we're always looking at light that's a little old. But usually that doesn't matter. Jupiter's the same as it was 40 minutes ago. The sun's the same as it was 8 minutes ago. Who cares? When we start looking at galaxies, even stars in our own Milky Way, we're seeing them hundreds to thousands of years ago. And then when we look at really distant galaxies, we're seeing them as they looked billions of years ago. So it's like collecting a snapshot. It's a little bit like getting photographs in an old dusty bin, and those people in the photographs are long dead, but you're getting this snapshot in time of like, oh, these are Civil War photographs. Okay, that was a long time ago. but you're getting a snapshot of what things were like then. And so that's what this is. This is a snapshot of this particular galaxy as it looked 12.9 billion years ago. And as for what happened to this star, it is long gone. Stars like that are dozens of times the mass of our sun, they only last millions of years.
Okay.
They burn all their fuel really fast and then they explode as supernovae.
Gotcha.
So, and that galaxy probably merged, just going by what typically happens through cosmic time, that galaxy probably merged with several other galaxies and is embedded within a structure that's much, much bigger and more massive, and that has accreted a bunch of different galaxies together today. So today, it looks very different, but all we have is this snapshot of what it looked like then.
Okay, all right, awesome. Yeah, hopefully that helps answer your question. Okay, so one question I actually have, Patty, is kind of a big one, but I'm just curious what you think. Like, why do we study stars in general?
Oh, that's great, because there's so many different answers to that. I think, in particular now, one of the driving scientific questions of our era is to find planets around other stars that look like they could be Earth-size or Earth-like. And we want to not only find those planets, but we want to interrogate their atmospheres, find out what's going on in the atmosphere. Do they have water vapor, which has been so important to life on Earth? If you follow the water on Earth, you find life. And the other way around, if you see life, there has to have been access to water. So astrophysicists and astrobiologists working together are really aiming towards building the next great observatory beyond Webb that would be able to look at a nearby solar system, block most of the light of the star, and then look at the spectrum of the planet to start looking for things like water vapor, carbon dioxide, methane. But the trick is that you only know as much about that solar system as you know about the star. You can't really say much about the planets unless you know a whole heck of a lot about the stars. So when we study stars, we learn a lot about not just our sun, but its place in context with other stars. And we also learn about the areas where planets can form and do form. We talked a lot about the star Earendel, but it's this massive star, and as Jane said, it's only going to be around for millions of years, and may not be enough time to form anything that looks like a solar system with planets. On the other hand, we see other stars in our own Milky Way that are much, much smaller than our own sun. And they seem to form small planets routinely. We find the small planets around the small stars. So we really need to be able to put all of these stars into context so that we can understand those planetary environments and go after that Earth 2.0 that we're all kind of crossing our fingers.
Yeah. Okay, great. That's awesome. All right, so we've gotten a couple more questions. Let's see. So, all right. Let's see. How likely is it that we might find more lensed stars like this? Or are we able to sort of predict that?
Sure. So there are a couple other lens stars known. They're still pretty rare. We're still at the level where each one's a paper, right? We're like, yeah, discovery, I found a star, right? So we're not in the this often happens in astronomy. We find a couple of things, it's a big deal, and then we get to the place where we can build catalogs, where we can do it systematically and look at populations. We're still at the stage where this is really hard to measure and hard to find. The way to find more is to study more lensed galaxies, is to do systematic surveys from more bright arcs. The lensed galaxies, right, the cluster, and then the lenses, the cluster, and then the lens galaxies behind them. And so there are a number of new and upcoming surveys of the whole sky, deeper than the current surveys that we have. And those surveys, like you would expect, are finding more lensed galaxies, and that will enable us to find more stars, with individual stars within those galaxies. It's a super rare thing, and so you have to go search a lot of haystack to find those needles.
Okay, cool. Let's see. So I think, Jane, this is probably for you too, because we've got some questions about Webb. So would Hubble or Webb be useful in observing nearby exoplanets, or what can you say about that? Or actually,
that's a Patty question.
Okay. Awesome.
They're actually both really useful.
Okay.
And I think one of the coolest things about Hubble, we were talking about how it was launched 30 years ago. We didn't know of any exoplanets for sure when it was launched. There were a lot of people that were hoping they could find it in their data, and they knew that there probably should be. There was under vigorous debate if we would ever be able to detect something so small that doesn't give off its own light. And also the telescope wasn't designed to do anything with exoplanets because we didn't have any, examples to design it around. And yet, there are planets called hot Jupiters. They're the size of Jupiter, they're very close to their star, they go around very often, some of them even transit. You can use Hubble to actually take a spectrum of that planet passing in front of its star so that you can look at the light that passes through the atmosphere of the planet and start to tease out what that atmosphere might be like. Does it look like Jupiter with all those clouds in it? Does it have, what's in it? So Hubble's actually been put to the test and pushed to its limits in that way for exoplanets already also. But as we were talking about before, it's got ultraviolet and optical, so that limits where you can really look in its spectrum. What's really cool to us, what we really want to go after, are things that are in the near infrared, things that Hubble is not good at. We really need something like the James Webb Space Telescope to let us go down to smaller planets because they're dimmer, they'll have less light output, but also the wavelengths of things like water vapor, of methane, of ozone, of oxygen. They're going to be found preferentially in the JWST spectral band. We can't wait. There are something like 60 exoplanets that are going to be looked at with the James Webb Space Telescope in the first year of operations, and some of them are specifically for going for those smaller planets and looking at how that atmosphere interplays with the starlight so that we can figure out what the elements are of the atmosphere.
That's amazing. Thank you. Okay. All right. Well, I think we are probably running a little bit on time, so we're probably going to have to call it a show for now. But thank you all so much for sending in these questions. Thank you guys for joining us and telling us more about this awesome Hubble discovery. If you want to learn more, please check out nasa.gov/Hubble, and as always, follow us on social media here on Instagram or on Facebook and Twitter, also at NASA Hubble. Thank you guys so much for tuning in, and have a great weekend. Bye, everyone.